Okay, welcome back, students. Welcome to another week of Chemistry of Everyday Life. This week, we are going to go into starting from this week, we're going to go into more specific about how chemistry affects different aspects of our different categories of our lives. So, for example, we'll talk about the environment this week, we'll talk about pharmaceuticals, and so on and so forth. So, the weeks prior to this, we've been focusing on specific topics like very focused on different topics in chemistry, but those are the foundational topics. So we'll use that what we learned from those past weeks and apply it to the weeks going on forward as we talk about different topics. Okay, so having said that, welcome. We are going to talk today about how chemistry affects our environment, and we're really going to focus on the water, a very special molecule. So we'll talk about the chemistry of water primarily today. One aspect of water that makes it such a unique compound, and that property is its hydrogen bonding. When we talk about molecular compounds, we talk about different intermolecular forces. Okay, the word inter meaning between compounds. So that's the attraction between different compounds. And we found out about some compounds being nonpolar and polar, right? So it turns out water is a polar molecule and an extremely polar molecule. So much we call that hydrogen bonding. And because of this property, or because of this fact, water displays various different properties that make it a universal solvent. It makes it ubiquitous in nature and allows for life to happen. Right? So that's the first fact, that water is the medium for biochemistry, for the chemistry of life. On top of that, water has a high boiling point and also a high melting point. Okay, so that's very important and it's very perfect for Earth, so that water is a liquid at room temperature and atmosphere. Okay, and another property is that water has a high specific heat, so allowing for absorptions of heat without raising its temperature too much. And lastly, last property we touch upon is that water has as opposed to many other molecules, when it is a solid, it is less dense than it is a liquid. Okay, so we'll take a look at all of these properties and how that supports life on Earth. Let's talk about water. So what is the formula for water? The formula for water is H2O. So it has two hydrogens and one oxygen per unit per molecule. All right. Can you remember how to draw the Lewis structure for water? Hydrogen would have one valence electrons, one valence electron each, and oxygen would have 6 valence electrons, right? So that's a total of 8 valence electrons. Oxygen appears only once, so it must be in the middle. Also, hydrogen can only bond with one thing at a time, so it cannot be in the middle. So we have oxygen in the center connected to the hydrogen. So using those two bonds, we have used 4 electrons. So it has 4 left. So where we're going to put the last 4 electrons. We're going to put them as a lone pair on the oxygen. Okay. Now, so this is a Lewis structure of water, but it doesn't tell you the whole story, right? Because the Lewis structure just tells you how atoms are connected. It doesn't tell you the shape of the molecule. And the shape of the molecule is very important for the polarity of the molecule. Seeing the molecule as is right now, it is very flat. Yeah, two-dimensional, right? And remember that electrons are negative, right? And negative, right, to repel each other. So if we draw it flat like this, the farthest away the electrons are from each other. And remember, electrons, this is an electron group, that's an electron group, this is an electron group, and this is an electron group. If you focus on the oxygen, how far away are those electron groups away from each other? You see that they're 90 degrees. So it turns out, if it's flat molecule, the farthest it can be from each other is indeed 90 degrees. But remember that life happens in 3 dimensions. So it can be in a shape that is going to make it farther away from each other, more so than 90 degrees. And that shape is called tetrahedral. So let me draw that shape to remind you. If you have a center like that, you have 2 groups that are flat in two-dimensional in that angle, and one that's coming towards you, and another group going away from you. So that's called the tetrahedral shape. And indeed, when we draw it in that three-dimensional form, the separation of the electron groups has increased to 109.5 degrees, or 109 for short. Okay, so that's the best shape it can be. Now, if you put in the hydrogens, you can see now that this molecule is indeed not a straight molecule, right? It's not a linear molecule, but that shape is called a bent shape. Now, let's focus on the electrons. We have 2 electrons here and 2 electrons here. Okay, so the electrons tend to be on the one side of this molecule, as drawn is on the right-hand side. But even further than that, remember that oxygen and hydrogen, even though that's called a covalent bond, they are sharing the electrons, right? But it's not an even share of electrons. It's quite uneven. It turns out oxygen is more electron greedy, more electron hungry. So it's going to pull the electrons towards itself more, even though those 2 electrons are shared between it takes the lion's share of that electron. And we can connote that by drawing an arrow towards the oxygen in both cases. Notice when I do that, the electrons are being drawn towards oxygen, and oxygen itself also has these 4 electrons on itself, right? So it turns out the right-hand side, or at least on one side of the molecule, is very negative, right? So we can signify that by drawing that negative sign. Meaning that on the other hand, on the other opposite side is devoid of electrons. So we can draw a positive sign on that side. Now, if we can just simplify this molecule and draw it like a magnet, yeah? If we can just draw like a magnet, we can say that one side is negative and one side is positive. Negative meaning the electrons reside on one side of the molecule more than the other. Because it has 2 opposite sides, this is what we call a dipole. If a molecule has this kind of dipole characteristics, we can say then that molecule is a polar molecule. First, we have to establish that water is indeed a polar molecule. So how does that make it a universal solvent? Okay, imagine you have sodium chloride, NaCl. NaCl is cation and anion. One is positive charge, one is negative charge. So that's why they love each other. They stick to each other because of that opposite attracts principle. Right? So how is it possible that water can pull these molecules apart, pull these ions apart? I mean, there must be something to compensate, right? So sodium loves chloride because of that negative charge. So somehow water has to have something that can compensate that negative attraction. Remember how we said that water has both a positive side and a negative side? Well, it turns out because sodium ion, the cation, likes to be attracted to negative things, water faces its negative side, its electron-filled side, towards sodium ions. And because water is such a small molecule, it can have many water units around and surrounds the sodium ion. Like so, really encapsulating and making sodium happy. Because remember, sodium was only happy if it was attracted to that chloride negative charge. But now it has a whole bunch of negative charges that it can interact with. So that makes it happy. But chloride also can be made happy because water has a positive side also, right? So the more or the less electron-rich side of water, the hydrogen side, can now interact with that chloride, the negative chloride ion. So there you go. Both of these ions are now solvated, surrounded by the respective sides that it likes. Sodium likes the negative side, chloride likes the positive side. And this, you can extend this to many ions and also even molecular compounds. If a molecular compound is indeed a polar molecule, right? So it has a negative side and a positive side, that molecule itself. Water can do the same thing. Water's negative side can interact with the positive of the compound in interest, and its positive side, and vice versa, can interact with the other side. Okay, so that's why water, we say, is a universal solvent. It can solvate many things. The only thing that it cannot solvate is what? Non-polar molecules. Remember that we said that like dissolves like. So polar molecule will dissolve other polar molecules. But so water cannot dissolve non-polar molecules. For example, we can say oil and water do not mix, right? When we mix water and let's say an oil, the interaction of water and oil is not there. It rather likes to be by itself. So the water, it's more happy interacting with one another. The oil is more happy interacting with one another rather than mixing. That's why water and oil do not mix. Okay, our next point is that water has a high boiling point and a high melting point. So why is that? Okay, so it's for the same reason, because water is a polar molecule. Is it attracts itself to another molecule. So for example, if we had water as that dipole, it can be attracted to another molecule with itself, right? So that's what we call the intermolecular force. The opposite attracts. The positive side attracts with the negative side. The negative side attracts to the positive side. That attraction is so strong because of the hydrogen bond. Remember, hydrogen bond is just a extreme, very strong version of that polarity. But because of that very high attraction bond, it takes a lot of energy for water to be broken apart, right? Because remember, when we give something energy, it's like giving it motion. And the more motion it has, the more it's able to wiggle around and kind of break away apart. So because of that strong attraction in water, we need a high amount of heat to evaporate it, for example. Okay, so that's why it has a high boiling point. And now this is important because, like as we said, water is the solvent on Earth. So imagine if it wasn't a liquid, it was a solid, for example, or a gas. Those two states of matter are not great solvents, right? Because for reactions to happen, molecules must be able to move around quickly, but kind of in a contained, concentrated state. So being a liquid is perfect for that because a liquid has an attraction, that's why it stays together, but it's still be able to move around. Therefore, the molecules that are interacting can also move around. If you were in a solid state and solid was your medium, everything is basically frozen. There's not much movement. If there's no movement, chemicals cannot kind of come into contact and react with one another. Now, on the opposite side, if it was a gas was the medium, interactions between molecules are less likely to happen because they're so far away from each other. Right? That's why water being a liquid at room temperature and atmosphere gives it a very good, makes it a very good medium for reactions to happen. Okay, so that's the second point. The third point here is that water has a high specific heat. Again, this comes back to this hydrogen bonding. Specific heat just is a quantity, is a quality of how much you can raise a temperature of a substance by 1 gram of it by 1 degree Celsius. Okay, so the more bonding molecule has, the more stuck together it is, right? So, and temperature, increase in temperature is just talking about the movement of a substance at the molecular level. So water, because it's so highly attracted to each other, is kind of stuck together so much strongly that it requires a lot of heat for it to wiggle apart, right? So that's why water can absorb a lot of heat without moving that much, aka increasing in temperature. And you can see this apply in our everyday experience. When you go to the beach, for example, when your bare foot touches the sand versus when it touches the water, is there a marked difference? There is, right? But why is that? Even though both of that substance is receiving the heat from the sun at the same rate, right? The sun shines on everything kind of equally, right? Without prejudice, it just shines everywhere. But why is the sand so much hotter than the water? Right? That's the reason. Is that water has a high specific heat, whereas the atoms, the minerals, the metals in the sand has a very low specific heat. So anytime the sun gives it heat, it raises temperature fast. Whereas the water has that hydrogen bonding that makes it the molecules stick together without budging, without moving, and therefore without raising its temperature. Water can receive a lot of heat without raising its temperature. And we are grateful for that because if it weren't for that, water would just all evaporate out and we won't have water as the liquid that we know it as. Okay, and the last point we have here is that water has a high density for liquid and it expands when it freezes. In most substances, when it is at a solid state, as you can tell, it kind of contracts and therefore it's more dense. And therefore, more dense things will sink to the ground, right? But water is quite different. When it freezes, when it goes into its um, solid state, it actually expands. And the reason for that, again, is the hydrogen bonding. Because in a liquid state, hydrogen bonding is free to move around, and that movement around can make it kind of squeeze together even more. But while it's in a solid state, it's kind of frozen and kind of cannot have that closer interaction. And therefore, it is less dense. What do you know about things that are less dense? They float or do they sink? They would float, right? So imagine when we go to the Arctic, right? We see where there's ice there. Ice is basically frozen water, right? Where's the ice? It's on the top, right? It's on the top. It's on the top floating, and the water is on the bottom. Or you just go to a lake, right? In the winter, right? Somewhere really cold. When the lake freezes over, does it freeze from the bottom up? It doesn't, right? So it freezes from the top down. There's many reasons for that, but one reason, even if it does freeze, the ice would just float to the top, and this is very helpful because imagine that provides for life, right? Because if it freezes from the bottom up, everything that lives in that water would just basically die when the lake freezes over. But it doesn't; it freezes from the top, and so that there can be water below that the animal, like the fish, can still live. And it turns out that freezing keeps the bottom from even getting colder. So that's another property of water that makes it very, very useful for life. All right, so I talked about the specific heat a little bit earlier, but here's a chart to help you kind of compare the specific heats of things. You have here aluminum at 0.1216 calories per gram degrees Celsius. And let's compare that with water, which is 1. Notice all of these metals and all of these other compounds like ethanol has very low specific heat. You can also see this in your daily life. When we cook with something, we use a metal, right? Because that metal has a low specific heat, so it will rise in temperature much faster with the amount of heat that it receives, which is good because then we want to transfer that energy over when we cook. We don't want something that resists temperature change so much, right? Right. So we said that water is ubiquitous. It's everywhere. Water is universal. And it's super essential. So let's see how much water do we have on Earth. So we see here in this first graph, this is talking about the total water we have on Earth. 95 or 90, more than 96% of it is in the oceans. What does that mean? It's salty water. Okay, so leaving us only about 2.5% being fresh water, water that we can use in human consumption, for example. Now let's zoom in onto that 2.5% and break that down. Of the fresh water, 68.7% of that is trapped as ice, as glaciers in the Arctics. So that's not very useful at the moment. Whereas we have 30% of that is in the groundwater, so deep underneath the earth, but it's not that deep because we can still tap into it, is 30% of fresh water. So only 1.2% of that is on the surface, meaning like freshwater lakes, ponds and streams and rivers and stuff like that. It's only 1.2%. So that's the percent that is quite more readily available to us. Now you zoom into that perspective of the surface water. Most of that, 69%, is again part of the ground in a very cold climate called the permafrost, whereas 20% of that is in the lakes, and then so on. You have that there. So water, even though it's universal, even though it's essential, is quite precious for human consumption, right, or human use. It just dwindles down as we go into these charts. Okay. So it is quite universal. It is everywhere, water everywhere, and because of this thing called the water cycle, and because of the fact that it can go in many different states, solid, liquid, and gas, it then can be distributed throughout the Earth. Okay, let's start here with water just being in the ocean because that's like we saw earlier is where most water is. Now, as the sun, and the sun is a driving force for this cycle, really, as the sun beams its light down, its heat down onto the ocean water kind of the water on the surface heats up. The water molecule that is attracted to each other as a liquid state gets to receive more energy, and then so much more energy that it breaks the hydrogen bond and kind of it escapes the liquid phase into a gas phase. Right, that happens in oceans, that happens in the freshwater lakes, everywhere there's a surface of water, even like puddles, right? In the puddle you have in your garden. That's called evaporation. And evaporation is that water becoming from a liquid molecule to become a gas molecule. So it has a lot of energy, that water vapor molecule. So it just is vaporized into the air. You can't even see it anymore. But when there's a lot of it that comes together, these water molecules, gas molecules that come together, and it's cold enough in the atmosphere, they then, because once it's cold, it loses its energy, right? When it loses energy, then it relies back on that hydrogen bonding intermolecular force. So it kind of condenses together. It comes together. That's why we call it condensation, and that's how we see the clouds. And at one point, that clouds cannot hold that state anymore. Then it just breaks down, and we call that precipitation, when the rain goes down as snow or as rain, right? Water. So that's precipitation, and that precipitation is spread everywhere because that cloud is spread everywhere around the globe by the winds, right? So that cloud can travel thousands and thousands of miles to fall down rain on a totally different area of the earth. So it can, when it falls down, first it can replenish the oceans or replenish the lakes, but it also can go down, seep into the earth as groundwater. As we saw earlier, a large part of fresh water is indeed groundwater. And when that groundwater, so that groundwater can be locked there and we can tap into it, like when we dig wells, for example, that's how we tap into the groundwater. Or it can just flow down into the oceans, into the lakes again. And then that cycle begins once again. Okay, so that's the water cycle. Now, because that water cycle is everywhere, it, along with it, can be contaminated. It can be touched and diluted with other substances that are not quite helpful to the environment or to our health. So let's first talk about natural contaminants. Contaminants that are just happening naturally in the world, right? Things like gases can dissolve into it, like radon is a gas that's from the earth that can be dissolved into the water, and that's a radioactive gas. You can have other dissolved ionic minerals like calcium, magnesium, and iron. We see that. We call that hard water when we have these ions in our water system. So that's natural and that's normal. And you can see this when hard water effect when you have when you take a shower, for example, in a bathtub, and you over time, all right, you can see a buildup of this like crusty salt. Right? That's basically the calcium and the other dissolved ions that's in your tap water. It builds up over time. And then we can also have organic matter that's contaminating our water sources. For example, we can have microbes like bacteria, viruses that's in our water system, and animal waste, right? Can also be part of the natural contaminants. And in fact, 80% of illnesses around the world is caused by unclean, unsanitary water consumption, water usage. So that's unfortunate. Okay, so let's take a look at the water usage in terms of aspects of our lives that we use it. I'll talk about in terms of the United States here, 34% is used in agriculture, whether that be to water the plants or to irrigate, yeah. 12% is used in our household, drinking, bathing, for example. 5% is used for industry. And another part of industry, a whopping 49% is used in power plant. Remember when we have power plant, it's generating a large amount of power for us, so it gets really hot. And when things get hot, it's not good. You can have a meltdown, for example. So in order to prevent that, you have to cool it down. What's the best cooling device? Water. Remember, because water can absorb a lot of heat. Remember, because of that high specific heat, it can absorb a lot of heat without raising its temperature much. So that's why water is a great source for cooling down power plants. Now, because of all that contamination that we just talked about, we need something to regulate and help us kind of make sure that things are going to be safe for us to drink and use in the water. So the EPA in the United States, at least, the Environmental Protection Agency, is created for that. For example, not just water, but other things, but water is one of them. And the Safe Water Drinking Act of 1974 establishes two categories of contaminants, right? There's something called a primary contaminant and a secondary contaminant. And based on these categories, water will be tested and then be treated in order for us to be safe to use as in our household. So let's talk about the primary contaminants. Some example of primary contaminants are like mercury, lead, stuff like that. They tend to be toxic in even small amounts. And we'll talk about the concentration units in a bit. Oh, right now, actually. So they are measured in what is known as ppm, parts per million, or ppb, parts per billion. Like, for example, when we talk about percentage, let's say 5%, that's 5 parts per 100. That's cent per cent is 100, right? So 5 out of 100 is 5%. Well, these toxic components are so toxic in a very, very small amount that percentage doesn't really give it justice. So instead of saying 5 out of 100, we say, let's say 5 ppm will be 5 out of a million. Let's say 5 parts out of a million water molecule. It is already dangerous for these substances, as an example. Or even when it's even more toxic, we go to ppb, parts per billion. 1 part for a billion of another part. A billion water molecule, if you have just one thing of this, it will be dangerous, for example. Okay, so that's how we measure these small contaminants. And so because of when they are primary contaminants, the EPA has something called an enforceable limit called the maximum contaminant level, MCL. Okay, so here's some example. Mercury is an example of that. Arsenic, you don't want any of that in your drinking system, right? That's usually coming from the agricultural byproducts. You can even have uranium as another example, because that's a radioactive contaminant that could be harmful, even small amounts. And we can also have microbes be in this list. Microbes being like E. coli and stuff like that, bacteria, viruses. On the other hand, we have secondary contaminants, and this is usually it's not as dangerous, but it does get regulated because it does affect the color, the taste, the smell of your water system. For example, we have here iron and zinc. They're not harmful to us to the same extent as the other ones, but they do affect the flavor of your water system. Okay, so going back to why that's important, one example is because you can have waterborne diseases like microbes, including viruses, bacteria, parasites that can be in the water system. It turns out that unfortunately, more than 800,000 people die a year due to unsanitary water usage. There are a lot of places around the world do not have a good water system that gives them fresh and clean water. And so oftentimes they die just because they are infected with some kind of bacteria, and that just causes, they just die from diarrhea, just being kind of dehydrated from these diseases. So oftentimes the treatment will be medication, antibiotics, even some vaccines are helpful. Now, if you're fortunate to live in a place that does have good water system, it's relying on not the treatment of it, but the sanitizing part, not the after you get the disease, but even before you get the disease. So that involves filtration, filtering out the bad stuff, killing the bad stuff off, boiling it, or killing with chlorine. And we'll talk about this in more detail in a little bit. All right, so now let's talk about some examples of contaminants from a chemical perspective. So we talk about here first acid rain. So what is acid rain? Acid rain is basically when you have these gases from factories that releases nitrogen oxides, various versions of that, sulfur oxides. The X just means it has various numbers of oxygen in it, or carbon monoxide or carbon dioxide, right? They are released when we burn things in power plants or in vehicles, right? Gas vehicles. Because of that combustion, it creates these molecules that are in the air, and these molecules that are in the air gets incorporated into the clouds, and when they water, and then so it rains down acid. Okay, so for example, if you have a sulfur oxide, it interacts with the water molecules, becomes sulfuric acid. The nitrogen oxides becomes nitric acid. The carbon monoxide and carbon dioxide becomes carbonic acid. So all of these are just acids that in the water that rains down on us. And acid rain is it's not good. For one, it kind of erodes monuments or erodes buildings that has like limestone or kind of some kind of mineral as their base, as their foundation. So as you can see, if you see a monument out there that's kind of being withered away, kind of whittled down, that's because of the acid rain. Acid rain can also cause ponds or freshwater lakes to change its biochemistry and ecology there. Another chemical contaminants that's not as scary is the hard water. I mentioned this earlier. Minerals can also be dissolved in your water system, like calcium, magnesium, carbonate, and iron. All of these is contributing to what makes hard water hard water. And I said earlier how we see this in a bathtub or sinks where there's just a ring of minerals that deposits. That's when you know you have hard water. Soft water is the opposite when you don't have these ions in it. Another place of contaminations from chemical perspective is from the agriculture. When we use it as fertilizers like nitrates and phosphates, they are also very soluble in water. So there's a runoff, and they go into when agriculture uses it so much, it has a runoff into the local lakes and whatnot. And it turns out that these fertilizers, when carried there, can be a fertilizing source for algae and stuff like that, which if it grows too much in these ponds, it just covers the entire pond, kind of suffocating the pond underneath, depriving it of oxygen, and that's not good. And that's called eutrophication. Another contaminant is lead, and we maybe in California have heard this. Also in the United States, we've seen lead being poisoned in our water system. Big headlines for that. But in California, specifically in my memory, just heard a story about how the water system in the Los Angeles school district is contaminated with lead. And the reason for that is because they used to make pipes out of lead, and 50 plus years ago, right? So these have worn out over time, so much that lead atoms are being led into the water system. So what happens, I think I saw one story, is one easy fix for it is that they have a person go in every morning to turn on the water at the schools, at the schools for a while, so that the first kind of run of water that comes out from the pipes is contaminated with lead, but then it basically flushes out the system. And then overnight, that lead contamination builds up again. So you have to do that process again, right? That's kind of the story I heard. It's kind of unfortunate and sad because lead poisoning can be dangerous. It can be detrimental to developing brains, so your development of children also. Okay, and here's one example of the concentration that we talked about, the ppb. So at 15 ppb, 15 parts per billion, is when lead is regulated, right? That's when the EPA says you have to do something about the lead levels in your water. Here's some other contaminations that we can see with its level. It's MCl. Arsenic there at 0.1 ppm. Fluoride, even though is add it into our water system to help us have healthy teeth. Too much of that is also bad. That's regulated at 4 ppm. Yeah, lead there, remember, was 0.15 ppm or 15 ppb. Benzene is a molecular compound that is used a lot in a lot in industry. Is regulated at 5 parts per billion. Yeah, if you live in a country where they don't regulate that they just dump that into the ocean, into the river. Um, yeah, that can be a carcinogen actually. Some other you can see here. Most of these are organic solvents people use in industry or in the labs, like toluene, for example, there. And so they're highly regulated. Mg per liter is the same as ppm. All right, so we have all these contaminations. What do we do with them? Um, so I think I'm going to end this lecture on what we do in most places in the United States where there's a system. I think you have to treat it if that source is serving more than 50 people or something like that. I forgot the numbers, but yeah. So if you live in any community, you have your water treated, and most of the time in similar manners. So first you get just the water from the rivers, the lakes, and whatnot, or from the groundwater. And the first thing you want to do is, because remember, water is a universal solvent, so there's a lot of bad stuff in there also we need to get rid of. So the first thing they do is something called coagulation. So they add aluminum sulfate and calcium hydroxide in there, right? So the job, so aluminum sulfate basically will bind with the calcium hydroxide to become aluminum hydroxide, and that just crashes out. It's no longer soluble in the water. Most things are soluble, but some things aren't, right? So aluminum hydroxide, Al, and then OH, will coagulate, will crash out, will precipitate, will become solid in the water. And because when it becomes solid, it kind of, at that moment, it traps the other contaminants along with it. The next step is flocculation, meaning that coagulation is just being swirled around so that it can be mixed and at the same time capture other contaminants. Now, that contaminant over time becomes heavy, so it will float down and settle down to the bottom. And the clean top part then can be siphoned off into the next stage of cleaning. And so this next stage of cleaning is called filtration, where it goes through layers of different materials that can absorb the various contaminants. Like it can go through coal, it can go through sand, and stuff like that. And at every level, these solids will absorb more contaminants. Now we can't that up to there we can get most contaminants out, but we still need to do one more thing for things that are still left over, things that could be harmful, like bacteria and stuff. So the last thing we do is disinfection. And so we can disinfect with the various things. We can disinfect with ozone. We can disinfect with chlorine. And so that's why you see pools, when they put in chlorine there, is to disinfect. But your water source that you drink, the tap water, is also disinfected with small amounts of chlorine, because the chlorine can kill bacteria and other microbes. Another way to kill them is UV light, but chlorine is better because it stays and then it works longer time, even because when you shine a light on something, it only works at that one time, right? It won't work later on. But add chlorine, it works a little bit more time after that. All right. So after you do all of that, you get clean water, and that clean water comes into our home, right? That's the hope, right? That doesn't happen all the time, and that's why we see things like the Flint, Michigan water crisis. Some of these steps were not properly regulated or done, and it was it leads to unfortunate catastrophe where people had to rely on bottled water as a clean source. Yeah. All right. So that's our lecture on water. The bottom line is water is universal. Water is everywhere, ubiquitous, and water is essential. And water has a very cool chemistry because it can do all of that.